Alright, so we're going to finally finish up our chapter on community and ecosystem ecology by taking a look at some nutrient cycles, and we're only going to look at a few of them. We're going to look at water, carbon, nitrogen, phosphorus, and sulfur because those are kind of some of the main ones that have the biggest impact on what the living world has to deal with. Nutrients, of course, are things that are kind of small-ish things, elements, small molecules that are the basis of every living thing. They're the things that form the molecules which make up our bodies, the things our cells use to function, and so forth. So very, very important things. Macronutrients are the things I mentioned a second ago: carbon, hydrogen, oxygen, nitrogen. We need lots of those things. So whereas those are large quantities needed, micronutrients are things that we need in much smaller quantities, like sodium and chlorine, potassium, iodine, all kinds of trace minerals you need in very small quantities to be healthy. We're going to focus on the big ones though. All right, so what we're dealing with here, sometimes called nutrient cycles, other times called biogeochemical cycles. It's kind of a funny made-up sounding name. I always kind of thought it sounded like it was made up. But if you think about it, it's actually got some meaning behind it. I mean, these cycles involve not only living things, so there's the bio part of the name, they involve geological processes at times, and they also involve chemical processes. So they're really kind of dealing with all three of those aspects of what goes into an ecosystem. These are going to deal with pathways the nutrients follow to go between the living and non-living parts of the ecosystem. There are places where at times these materials are stored up in large quantities. We tend to call those reservoirs. So, for example, water, you've got the oceans, right? For carbon, you've got calcium carbonate locked up as limestone. For phosphorus, very often phosphorus and sulfur, both really, are locked up in rock form or mineral form. So they tend to be in the abiotic part of the environment, large quantities stored up, often for long periods of time. So we're going to start off looking at the hydrological cycle, which is the water cycle, effectively, how water gets through the environment. The main driver of the water cycle is the sun. So as sunlight evaporates water, water can be lost from the oceans. It can be lost from water on land. It also is involved in distributing water in the form of precipitation. So solar cycles drive also precipitation cycles to some degree. So when that water condenses in the air and begins to fall, that precipitation then supports the terrestrial ecosystems like we saw in our previous sections on the biomes. So from there we have cellular metabolism, we have nutrient flow. So when you see erosion of rock, that's being driven by water, obviously, in most cases. Global distribution of heat and energy, like we talked about with the jet stream, and also ocean currents that distribute heat and energy up to northern latitudes and southern latitudes to help maintain life there. The major reservoirs of water, obviously the oceans for salt water. Freshwater is very limited compared to saltwater. As we'll see, freshwater is one of the most limiting resources we have on the planet, believe it or not. Freshwater reservoir, the biggest one actually is in the form of ice, believe it or not. So big glaciers and ice caps and things like that contain massive quantities of fresh water, and also groundwater. Those are kind of our two main sources of fresh water. When you think about, rivers and lakes and streams and ponds, those do represent fresh water, but they're very, very limited in quantity as compared to some of the other reservoirs. This graph here is very instructive and really kind of scary when you think about it. If you look at the total amount of water on the planet, roughly only 2.4% of it is fresh water, and that's the water that living things have access to maintain themselves as living things. If we take this tiny little narrow wedge of fresh water and blow it up, we see that most of it, 87% of it, is locked up as ice and snow, so it's not even really available for living things because most things don't want to chomp on ice to get water out of it. That water is effectively locked up over a long period of time. Groundwater is the other kind of big one. It's about 12%. And then fresh surface water, which represents waters, lakes, streams, soil moisture, moisture in us and animals and plants and so forth, that's only 0.8%. And so if we blow up that little tiny narrow wedge, then we see this over here. All right, these are the other places where we have water. In addition to moisture in plants and animals, soil moisture in freshwater lakes and reservoirs, there's atmospheric water, there's wetlands, and there's rivers and streams, which only make up about 0.6%. So the total amount of fresh water on the planet that's actually available is very, very small. 0.8% of 2.4% is actually available to be used by living organisms. And so it's not surprising then that we worry a lot about fresh water because it's something we have to have. I mean, you can't get around it. Fossil fuels, if you had to, you could live without them. You could find alternative sources. You could use less of them. It would be doable. Water doesn't work that way. You really kind of need to have water. And so a lot of people think that down the road, before too long, within a few years, maybe a couple of decades, most wars fought on planet Earth are not going to be over other resources. They're going to be over fresh water because countries, people need to have them. You can't get around it. So here's kind of a picture of the hydrological cycle. We see the driving of evaporation from water on land, transpiration from plants, evaporation from the ocean. Eventually, that water vapor gets distributed. A lot of it falls right back into the ocean again, but some of it falls over land. And when water falls over land, it's going to kind of run along here. It's potentially picked up by plants or animals. It could flow into a river back into the ocean. It could kind of eventually seep down through the soil and get into groundwater and then find its way back to the ocean, perhaps. So that's basically what occurs with the hydrologic cycle. The next one, after the hydrological cycle, we're going to see is the carbon cycle. But before we get there, we're going to take a look again at water scarcity because that is such an important thing. It's kind of outside the realm of the class, but in a way it is related. And it very much is related to, real issues with humans and what we're doing on the planet. The largest human-derived source of water consumption is actually agriculture. So water is used more for growing crops than it is for anything else. Anything else we do, farming basically is the biggest user of water as far as humans are concerned. A lot of what's been done previously is by using groundwater, aquifers, drawing water up from those and using that water to water fields. Now the issue with that is it's a finite resource. There's only so much of it, and those aquifers have been largely depleted based on people trying to grow crops in parts of the world that's really too dry to grow crops. They've done it because they've had aquifer, groundwater available, but there's less of that available, and a lot of it's also become polluted. There's a lot of things in the environment that have made their way into the groundwater that kind of make it unsuitable anymore to use as either drinking water or agriculture. Drinking water that's contaminated is actually consumed by a lot of people. Roughly, like 1/7 of the world's population drinks contaminated water of either chemicals or sewage or some other nasty thing that you probably don't want to think about drinking. We're really spoiled in the U.S. because most of our water is actually pretty good. We've got a lot of it, and it's still reasonably high quality. Most of the rest of the world doesn't have that luxury. There's a few places that do, but water is a very limiting resource for much of the world's population. All right, the carbon cycle, we're going to start off looking at it where CO2 is entering into plants through the stomata and being used through photosynthesis. Producers on land are getting CO2 from the air, basically. So by breathing in CO2 in the air, they can use that to make glucose. It's dissolved CO2 in the water as well if you're an aquatic organism. But then the primary consumers come along and they're going to consume, or omnivores come along and they're going to consume those primary consumers and take on carbon that way. Once those other organisms and the producers as well, because everybody kind of goes through cellular respiration, once we've had a chance to do that, then CO2 is going to be released back into the air. Some of the rest of it can be stored up. If you're a plant, you can store up a lot of carbon as cellulose. Other organisms store up carbon as other sources or other reservoirs of carbon, but eventually it's going to be released back into the community. When it's broken down by decomposers and detritivores, it can be taken into their bodies. It can also be released back as CO2 into the air again. So there's kind of this continuous picking up of CO2 by plants and then releasing of CO2 not only by plants but by animals and fungi and bacteria and everybody else that does respiration. But at times, some of that carbon doesn't get picked up. If organisms die at such a high rate that decomposition can't keep up, then some of that carbon gets locked up below ground for really long periods of time. And that's basically how how fossil fuels were formed. Roughly maybe 350 million years ago during the Carboniferous period. There were massive forests that died off, and the death of organisms happened so quickly that they couldn't decompose fast enough, so they sort of formed layer after layer after layer of dead vegetation. The layers beneath got compressed, and under periods of high pressure and high temperature were formed into both coal and oil, which is what we use as fossil fuels today. The reason why burning gasoline, burning coal, burning oil, those kinds of things releases so much carbon is because that's what those things are. Fossil fuels are stored up carbon that used to be plants a long time ago. And so when you burn them, when you oxidize them, that carbon then is re-released back into the atmosphere. It's just been locked up for the past 300 million years. It was always there. We're just re-releasing it back into the atmosphere. There's also carbon stored up as calcium carbonate, carbon is stored as part of calcium carbonate in limestone. Coral organisms make a calcium carbonate backbone, so to speak, and so they lock up calcium for long periods of time as well. That's another less substantial source of carbon that can be seen also. So we think about things on the planet that are both carbon sources and carbon sinks, and you really hear a lot about carbon because of greenhouse effect and climate change and those sorts of things. But carbon sources are things like cellular respiration in all organisms. There are things like burning of fossil fuels. There are things like decomposition. All of those things release carbon into the atmosphere. Carbon sinks are places where carbon is stored. So if we're looking at calcium carbonate, if we're looking at stores of fossil fuels that are being made, and they are being made slowly even today, that would also be a carbon sink. You could have even the wood of trees. Trees can live for hundreds of years, even thousands of years, and when they lock up that carbon inside their stems and their trunks, then it's unavailable to go back into the atmosphere, at least for a while. So that would also be more of a short-term carbon sink. The issue we're dealing with today, based on human activities, is the fact that humans burn far more fossil fuels and release far more CO2 than carbon can be taken up by natural processes. So even though we're still processes are still locking up carbon temporarily, we're releasing it way faster than it's being locked up. And so all that carbon in the atmosphere, the CO2 in the atmosphere, works as a really good insulator, absorbs and traps solar radiation, and now that, in addition to a few other factors, help to increase the temperature overall on the planet. So we think about global warming, we think about climate change. It's caused by not only CO2, but other greenhouse gases that can be released also. Right? But the carbon cycle starts off with CO2 and photosynthesis. There's a big component of cellular respiration as well, and then we add in the human element of burning of fossil fuels to really kind of top things off. Right, so that's the carbon cycle. We kind of see a few things here. We've got the producers taking CO2 out of the atmosphere. That can then be fed to various levels of consumers. All of these organisms do cellular respiration, so they're releasing CO2 all the time. Any sort of burning of fossil fuels, any burning of trees, any decomposition, all of those things are going to help release carbon into the atmosphere again. The nitrogen cycle is a little bit more complicated in a couple of ways. We really need nitrogen for two reasons. Number one is to make protein, first and foremost, and number two is to make nucleic acids, because they also contain nitrogen. Now, nitrogen seems like it shouldn't be a limiting factor because it makes up like 79% of our atmosphere. The problem with that is that atmospheric divalent nitrogen, N2 gas, is really, really hard to break down because the two nitrogen atoms in the nitrogen molecule are triple bound together. It takes a lot of energy to break that bond. It's very difficult to do it. So what we have to do then is find a way for plants to get nitrogen out of the atmosphere so that they can make proteins and therefore support the rest of the terrestrial and aquatic food chain. One of the most important ways this happens is by the activity of certain bacteria which can convert atmospheric nitrogen into ammonia. They have special enzymes they can use in certain conditions in the roots of some plants to split that trivalent nitrogen into two nitrogen atoms, which can then be taken up and converted as NH3 or ammonia. Other bacteria are what we call denitrifying bacteria, and they can convert ammonia back to either nitrites or to nitrate, depending on the process they're doing, and that also kind of affects the nitrogen cycle. Those things can be taken up by plants as well. Actually, those are nitrifiers also. The denitrifiers are ones we haven't seen yet. They kind of go back the other direction into N2 gas. So anything that makes ammonia, nitrite, or nitrate. So nitrite is this one, nitrate is that one. Anything that makes any of those three would be a nitrifying bacteria. They make nitrogen available to the plants and so forth so they can make their proteins. Leguminous plants, things like peanuts and soybeans and alders, have nodules in their roots that house the nitrogen-fixing bacteria in a sort of mutualism. We saw pictures of that, again, really early on in this chapter. It's a win-win association. The plants are getting nitrogen, the bacteria are getting a place to live, very specific conditions are met, and everybody's happy. In terms of our nitrogen, of course, we have to get it by consuming someone else. So the protein that we consume in our diet is our biggest source of nitrogen. So again, here's a plant. All these little kind of round spots on the roots are nodules that house those nitrifying bacteria and allow them to produce nitrogen, which can be used by plants. When organisms die, obviously that nitrogen can be reintroduced into the food web as well. Excrement and urinary waste contain nitrogen as well. They're kind of a fertilizer in a sense, which is why they're used as fertilizer at times. Another aspect, although it's a more limited one, way that nitrogen can get back into a food web from the atmosphere is through the activity of lightning. So when lightning strikes, all the atmospheric air in the immediate vicinity, that nitrogen is then split apart into its respective nitrogen atoms, and it can be used again as fertilizer in a way if it's picked up by plants. The place where humans have affected the nitrogen cycle the most is by burning oil. Not even really so much coal, but by burning oil, what we've done is we've put a lot of nitrogen-containing compounds in the air. That's one of the big components of smog, and that eventually will then lead to one type of acid rain. So we take this nitrogen, we dissolve it in water vapor, and we make something called nitric acid, which when it falls on land helps to decrease the pH of soil and water and can cause issues with other living organisms on land. The other way we've contributed to it is by using synthetic fertilizers. So by dumping massive amounts of fertilizer on farm fields, we've really kind of tipped the balance of what fertilizer would have looked like naturally versus what it looks like in terms of human agriculture. We've also planted a lot more nitrogen-fixing crops. These plants that do this are not especially common when you look at nature unaltered, but when we look at human agriculture, these plants are really heavily favored because we can plant these alternating with things like corn. So what people do is they'll plant corn for maybe 2 or 3 years, and then they'll mix in soybeans for a year to kind of get the soil back to its nitrogen-rich state and to a point where it can grow the corn again for another year. So we've kind of messed with things there as well. And then again, the fossil fuel aspect that I mentioned a second ago. So again, there's the nitrogen cycle. We can see it, primarily down here with the bacteria pulling the nitrogen gas out of the air, turning it into a form that can be used by plants. Plants can then pass it on to consumers through the producers and so forth. Any sort of burning of fossil fuels produces nitric oxide, which then turns into nitric acid, which is acid rain. Electrical storms produce nitrates as well. So there's all these kind of interacting features, geological, chemical, and biological, that contribute to all of these cycles, which is why we call them biogeochemical cycles. The phosphorus cycle is another one that's important. We need phosphorus to make aspects of cell membranes. So if you remember back in chapter 3, we talked about phospholipids. DNA and RNA, ATP, all those things also contain phosphate. So they are needed for living things, albeit in much smaller quantities than any of the ones we've seen so far. The phosphorus cycle is one that has a much bigger abiotic component. So for phosphorus to be released, what has to happen is there has to be weathering of rocks. There has to be some sort of erosion, water moving over land, breaking down rock, and releasing phosphorus, which can then maybe be taken up by living things. The phosphorus cycle is also a much longer one. It takes a lot longer for any given atom of phosphorus to make its way from, say, you back to the non-living part of the environment and then back into another living thing at some point in time. But again, these can be taken up by producers. Phosphorus, in addition to nitrogen and potassium, are three of the most limiting factors for plants. If you buy fertilizer, in fact, it's going to have some amount of phosphorus, some potassium, and also some nitrogen, some ratio. So it's definitely something plants need. And from there, like we've seen before with everything else, the phosphorus can be passed on to the consumers. Decomposition of those animals and plants then is going to re-release the phosphorus back into the environment, where it's probably going to get locked up in some abiotic sink for kind of a long time. Eventually it ends up in the ocean sediments, and then from there, for those ocean sediments to get back onto land might take eons before that atom of phosphorus eventually gets back into a living thing. It's a really, really long time before that sediment gets turned back into rock on land that can then be broken down by water, taken up by plants, and repeating. The phosphorus cycle has been most heavily disrupted by fertilizers again. There was a period of time, especially in the 1960s, when laundry detergents contained large amounts of phosphorus, and that was causing issues in aquatic systems because that phosphorus was actually fertilizing algae. So there was huge algae blooms that were causing big problems with freshwater aquatic systems, and so that those laundry detergents were eventually reformulated to contain less phosphorus, so they would have less effect on those aquatic systems. Again, phosphorus, much more of an abiotic component here. Phosphates are locked up in rocks. That runoff is then going to eventually break down some of that phosphate to get into the living part of the ecosystem. Producers take it up. It's passed on to consumers and detritivores. It goes back into the soil again eventually, and maybe even gets locked up in these sediments downstream as well. Rivers are continuously bringing phosphorus down. These sediments are going to stay down here for a long time, but eventually, if the geology is such that these rocks get pushed back up against above the level of the water, it could become, exposed to air, exposed to water again, and then begin to weather, release phosphorus, and have it taken up by plants again. The last cycle we're going to see is the sulfur cycle. Again, this one has a large abiotic component. Most of the sulfur is locked up below ground, either in rocks or in mineral form. Typically, sulfur is released naturally by weathering of rock and also by volcanic eruptions. Actually, volcanoes, when they erupt, release huge quantities of sulfur into the atmosphere, which can then eventually find their way into living things. Sulfur is actually a pretty complicated one because it can show up as all different kinds of sulfites and sulfates. It can show up as sulfuric acid in terms of acid rain, kind of like nitric acid formed acid rain. Sulfuric acid is the other form that we find in acid rain. Some of the things that we do, especially burning coal in this case, burning coal releases not only carbon but also typically large amounts of sulfur depending on the type of coal you're burning. Soft coal especially tends to have a lot of sulfur in it, and that gets off into the atmosphere and then eventually can later on produce acid rain as well. But again, it's fossil fuels that cause that to happen most substantially. So again, the sulfur and nitrogen are typically what are involved with what we call acid rain. So there's the sulfur cycle. Again, lots of geological component here, some chemical component, biological component above ground, lots of contribution because of volcanoes and burning of coal kinds of things. But that's the sulfur cycle in the extent that we're going to see it. All right, so finally we've reached the end of Chapter 19 on community and ecosystem ecology. Told you it was a long one, but we're done with it for now, so I'll wrap this up, get these posted, and we will start with Chapter 20.